Contrary to what Fourth Hour wanted, which they said, no video, we don't want to hear your voice. I am going to make a video of these notes. I'll make it short and sweet, which is the opposite of me, tall and bitter. Anyway, so we just wanted to make sure that you knew what series notation meant. So the sigma notation means sum, so you're adding some things. The number on the bottom, this could be I, N, it could be any variable. And notice a little discrepancy there. Oh no, I guess it's not a discrepancy. But what you would have is a formula in terms of the letter I after this, and you'll see this as we move forward. So that means sum of the first to the nth term, and that's what this S sub n means as well. That's how many terms I'm adding together in order to get your answer. So summation. So in other words, the sum of this little thing from 1 to the nth term, here is the formula, like I just said, in terms of I, and then input say it. So this is a sub 1. How do you get a sub 1? You plug in 1. 3 times 1 plus 4 is 7. This is a sub 2. How do you get a sub 2? You plug in 2. 2 times 3 is 6. 6 plus 4 is 10. And then up to the nth term, whatever that is, so if this would be like an 8, then it would be up to the 8th term. So 1, 2, 3, 4, 5, 6, 7. Who do we appreciate? 8. So this would be maybe the 8th term. 3 times 8 is 24 plus the 28. And then you'd have to physically write these out and then add them. But then in arithmetic, this is actually arithmetic with a common difference of 3, and geometric series, there can be formulas because they have patterns. All right. So anyway, this is a finite series because it ends at the term n, doesn't go to the infinite term. Mind blown. How could we add to the infinite term? Someone's jiggling my door here, freaking me out. Maybe I'm getting more toilet paper. All right. So write each problem using sigma notation. Use k for the index variable. So here's what becomes tough on this. Sorry, someone is coming in here. I gotta do something for a second. Blah blah blah. Hold on. Oh, goodness gracious me. Okay, and I don't want to do all of these. You can look at the key in order to get this figured out, so on and so on and so forth. So 1, 2, 3, 4, 5. We'll call this, you could call this either the 0 term or the first. It doesn't matter. Sometimes we start with the 0 term. You'll see this later. But if you call this the first term, then we'll say k equals 1. Second, third, fourth, fifth term. That's why a 5 is up here. So we should know that first and foremost. Second of all, how do we get this formula? This is arithmetic. These are going up by 4 as far as terms are concerned. So I should be able to remember from our AP arithmetic sequences relate to linear sequences. And the formula for that was, I'm going to do that work off to the side, a sub n equals the first term plus n minus 1 times d, the common difference. All right, and actually I should be using k because it does say k here. It doesn't matter, just variable usage. We could use any letters that we want. 4k minus 4 plus 5. So I believe that's 4k plus 1. I kind of did that real fast. Let me just make sure this creates the terms. Plug in 1, 1 times 4 plus 1. Plug in 2, 2 times 4 is 8 plus 9. 3, 4, 5. Plug in 5, 4 times 5 is 20. 20 plus 1 is 21. So this formula must generate these individual terms. This means sum those individual terms. So that's the difference between sequence. This is a sequence if I just have commas. When I add those terms together, then it becomes a series, which is a sum. All right, looking at this next one, this looks like it's geometric. How do I know that? 12 divided by negative 6 is negative 2. Negative 24 divided by 12 is negative 2. Or as I move forward, I multiply by negative 2 to get from this term to this term. All right, so I do have that. That, when we were looking at those terms, was a sub k. So some general term equals the first term, a sub 1, times some r raised to the k minus 1. That was that formula from back in the day. Sorry, my k value is -2. Now, why k minus 1? Because I want to be able to create this. When you have a listing of terms, we always call that a sub 1, the first term. So when I plug in 1, 1 minus 1 is 0. Anything to the 0 power is 1. 1 times -6 is -6. A sub 2, plug in 2. 2 minus 1 is 1. -2 to the first is -2 times -6, which is 12. 3, 4, 5, 6. You could plug in 6, do your calculations, beep, boop, bop, boop, and you end up getting 192. So since I said k equals 1, then 1, 2, 3, 4, 5, 6. This is 6 terms that I'm adding. Here is my formula. -6 times the r value, -2 to the k minus 1. All right. One note to self, we could, I want to leave this in it. When you have a listing of terms, we usually call this a sub 1. Now watch when we have later questions where k equals 0 is on the bottom. We'll handle that when we get to that one. All right, I said I wasn't going to do all these. Look at the key for 3. I don't want to go crazy with this. Expand the sum, determine the type of series, representative, arithmetic, geometric, or neither. I'll just tell you right now that's neither. This is an oscillating. Ooh, that's interesting. I wonder why they just didn't put -2 raised. I believe this is the same as if it was just -2 raised to the k plus 1. I plug in 3. 3 plus 1 is 4. -1 to the fourth is 1. And then 3 plus 1 is 4. 2 to the fourth is 16. I plug in a 3 here. 3 plus 1 is 4. -2 to the fourth is positive 16. So what I'm trying to get you to understand, this is geometric, even though we got this separated into 2 separate things here. This is equivalent to doing that. Little tricky there. This is not arithmetic or geometric. This is just 1 over 1, 1 over 2, 1 over 3, so on and so forth. This one is geometric with an r value equal to 4, right? Because it's 4 raised to a power. That's what geometrics look like. And then arithmetic looks like linear. This has a common difference of 2. D equals 2. Go ahead, list out a couple terms. You'll see, and I'll do that. 2 times 5 is 10. 10 minus 3 is 7. 6, 2 times 6 is 12. 12 minus 3 is 9. 7, 2 times 7 is 14. Minus 3 is 11. And then 2 times 8 is 16. Minus 3 is 13. So notice these go up by 2. That is the definition of an arithmetic sequence. So it's arithmetic, then evaluate the sum, just add these up. Equals. I don't feel like doing that right now. I'm going to go to the geometric. See, here we go. K equals 0, so 4 to the 0 is 1, so our first term is a half. Then the first term, 4 to the first, half of that is 2. 4 to the second is 16, half of that is 8. This is going to get big. Third, 4 to the third is 64, half of that is 32. Oh, no. 4 to the fourth, 16 times 16 is 256. Half of that is that 128? I hope I did this right. I don't feel like grabbing a calculator. I don't want to. All right, but anyway, multiply by 4. Well, I could just do that. 4 times 30 is 120. 4 times 2 is a darn tootin'. Multiply by 4 as I go up from these. And then just go ahead and add these and get an answer. Doink, doink. All right, so you get the gist there. So notice I went from the 0 to the 4th. This one I went from the 5th to the 8th, and I plugged in 5, 6, 7, and 8. Who do we appreciate yet again in order to list out those terms? Okay, now, is that page 1 only? Okay, page 2. You could read all of that, and then you could read about Euclid. Actually, I love the arithmetic sequence or series. That was developed by Freddie Goss when he was like 2 or 3 years old. A teacher gave him a busy stuff. I'm going to tell you this. So busy work. He said, "Oh, you little brats, you're driving me nuts, crinkling your water bottles in the 1400s or whatever it was, poking each other and get off your phones, get off your abacuses in 1400s." Anyway, so he said, "You know what, kids, just sit there and add the first 100 integers together and then give me that sum." This is a little side note from Mr. Samuelus. So what little Freddie Goss figured out was if he had the list of numbers, 4, 5, 6, then 98, 99, 100, and he had to add all of these up together, and then dot, 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 dot. So that's what the teacher gave as busy work. He understood that 100 plus 1 is 101. 2 plus 99 is another 101. 3 plus 98 is another 101. And what he figured is I paired these 100 numbers up. He had 50 sums of 101. That is the arithmetic series formula. And he figured that out as like a 2 or 3-year-old. All right, imagine that. But anyway, that's not on the test. Is this going to be on the test? Well, the answer is no. Okay, now there is a way that we could find the sum of a geometric series using a formula. We are not going to derive this. This is basically a formula you're going to have memorized. Okay, and that's what it is. So Freddie Goss had a formula for arithmetic, or at least he's given that credit for finding that. This is if the series is geometric. So if you have a geometric sequence, you can add that as a series using this formula. So how do I recognize that this is geometric? Well, you got to know the geometric format. The geometric format is first term times sum r raised to some power. I guess I'll use that as k. So if you have a common ratio, then it is geometric where you're allowed to use this formula. So this is geometric. I'm allowed to use this. We are not going to derive this. We're just going to shove it in your face, and you got to figure it out. Be careful. The first term is the first one that they're asking you to add here. So it is the first term from the 1st to the 10th. Look on our previous page. This is not the first term. And then this is the 0th term. So that counts as the first term in this. I could have used the formula to do this question. But careful, from the 0 to the 4th term, that's 5 numbers you're adding together. That's part of your formula. So now going to this, it's easy. From the 1st to the 10th is 10 numbers you're adding together. That's what this is right there. So the first term is, plug in 1. 1 minus 1 is 0. 4 to the 0 is 1. 1 times a half is a half. Oh no, fractions within a fraction. Half my students are going to faint. And then you take your r, which is 4. If it's a negative 4, you better put that in parentheses. And then it's raised to the n, which is how many terms you're adding together. From 1 to 10 is 10 terms. So it's 4 to the 10th over 1 minus 4. Oh boy, you got to sit there and wait till I put this on the calculator. Okay, you got to be really careful on putting these in correctly. You should at least make a little sense out of your answer. This is going to be quite a large number because my first term is a half, but then, was this the one that we just had up here? It was this one. So look at these first terms. This is going to start diverging and going pretty quick. All right, so I just noticed that. This is a mess here. I'm going to move this. Sorry, we're at 14 minutes. Oh, I'm really going to shut this down early. Hopefully my explanation is enough for specific parts that you can get this taken care of. All right, so I'm going to type this on my calculator. Oh, this is going to be a pain. I wish I had this up on my screen. So second quit. I wasn't prepared. Clear. All right. Oh, son of a, never getting this stuff going on. I think this is why people don't want me to do a video. Probably cause them anxiety when I exhibit my anxiety. I'm going to put 0.5 and then go from there. 1 minus. I cannot overemphasize. If that r was a -4, you must put -4 in parentheses and then caret it. But you know what? We're good. Caret 10th calculator takes care of all of our little things that we need to take care of as far as order of operations, and then 1 minus 4. You could have just put -3 there, and I don't think I needed those denominator parentheses. Okay, it should be a big number. There we go. Then there's that half. So 174, 762.5. I'm not dragging that on the screen. It'd be a waste of time. Okay, so notice it said finite geometric series because, well, you'll see later. All right, and I'll just do this one because it's more tricky. What's the 0 to the 12th term? That's 13 terms. Why did they do that? Because now look at this exponent compared to this one. You know, that's what they like to toggle between, all right? And these are both geometric. I do have an R value. I do have an R value. Hey, and there's that one that I told you. I plug in 0, I get 1. 1 times 4th is a 4th. So the first term is a 4th. Then it's 1 minus R raised to the 13th. Now what happens with this is this oscillates between positive and negative. So when you add those numbers together, they oscillate between, you know, it really is not a large sum. I mean, it may be because the numbers do start getting quite large. But yeah, just keep in mind what that means if you listed out the terms. They'd oscillate between positive and negative, so the sum will oscillate between positive and negative, depending on who the bigger number is when you're done. The 0th term is positive. The 12th term would be positive. So I'm assuming I'm going to have a positive sum here when I'm done. All right, let's slide this sucker over here. And then definitely calculator work. Or if it wasn't, it would just be, you know, like it would be, this is the answer in multiple choice. So just emulation of the formula there. So sorry if this is coming out of left field. I don't like doing that. I like showing you where things come from. I could show you the next part. I thought I hit minus there. There we go. Then remember what I said, -2 in parentheses and then carets. That's 13 terms there from the 0th to the 12th. And then I do want to close that off. That closes the first that first parenthesis. And then divided by 1 minus -2 is 3. Oh, I know a negative. Oh, I know negative to the 13th power is negative, but then you're subtracting it. So that's what I was saying before, that this is going to be a positive sum because the 12th term kind of takes over. Yeah, and that's kind of a small sum because it oscillates between positive, negative, positive, negative. Then you keep adding positive, negative, and it keeps oscillating between a positive and negative sum. So anyway, that's what's happening there. And then this is interesting. Write sigma first, calculate the sum. Write out sigma notation, and then calculate the sum. All right, this is said to be geometric, so I guess this is weird. So G sub 1 is 10, G sub 2 is 9. How do you get what it is to get from here to here? You divide backwards. So R is simply 9/10, and A sub 1 is 10. So the sigma series, you could choose whatever you want to do. I guess I will say, and we'll use, it doesn't say anything about rules. We'll go K through 1 to 15 because that is 15 terms. So this is one option. And then we call the first term 10 times 9/10 raised to the K minus 1. Because what we got to make sure is when I plug in 1, 1 minus 1 is 0. That to the 0 power is 1. 1 times 10 is 10. Plug in 2. 9/10 times 10 is 9. So it does work. Or you could do K equals 0, but then unfortunately you'd have to go to the 14th. That's 15 terms. And then it would be 10 times 9/10 just to the K. And there's your two options, all right, on that one. And then calculate the sum. I already showed you how to do that, so I'm not bothering you with that. The last one I want to do is this. I really should just show the key for this. what this shows is when you have a converging geometric series, that's a series where the last terms are getting so infinitely small that you are approaching zero on the last term. So you can look at the key on this and look how this is developed here. I'm just going to get to the brass tacks of it. This series converges because this R value is between 0 and 1. So the R value, absolute value, whenever it is between 0 and 1, you will have a convergent series. This one diverges because you're taking 2 times each term. So the first term, let's get this done. The first term is 5. And then when I plug in 2, the next term is 10. Then the next term is 20. Then the next term is 40. When you add these are going off into infinity. Next one's 80. This is going to get infinitely large. So what we say about this sum is it doesn't exist. This sum goes off into infinity. But on this one, 5's an unfortunate number here. First term is 5. And then 0.2 of 5, 0.2 is 2/10, which is 1/5. 1/5 of 5 is 1. 1/5 of 1 is 1/5. 1/5 of 1/5 is 1/25. What's going to happen, ... Essentially, a sub infinity is essentially 0. So what has happened is you've established the sum already. This sum exists. It actually exists as a concrete sum there. And I guess I could give you a couple indications of this and what actually occurs. You know what actually occurs? I'm going to write the full formula out. A sub 1, 1 minus R sub n over 1 minus R. But when this R is between 0 and 1, and you raise it to the infinite power, this becomes 0. And 1 minus 0 is just 1. So that's what's amazing. When you have a convergent series, when your R value satisfies these conditions, this formula will give you the infinite sum of that series. It's amazing. Determine whether the infinite geometric series converges. If so, if it does, find its sum. Well, look at this. 6 to 3, that looks like I'm taking a half, then a half, then a half. So this is 6 times a half raised to the n minus 1. That's what this formula is. I plug in 1, I get 6. I plug in 3, I do get 3 halves. 3 minus 2, 1 is 2. That's 6, 1/4. 1/4 times 6 is 3 halves. I kind of skipped around here. So this one converges. Therefore, the infinite sum does exist. So what is that infinite sum? I do like to, I guess I could write it like this. Doink, 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 doink. It doesn't say to write this, but I'm gonna use n. N-I-K, who cares? But the top says infinity. All right. And then what this is this formula then, 1/2 n minus 1. This formula then is the first term, 6, over, this is wild. You feel like you're cheating, 1 minus r. 1 minus r is a half. So 6 over a half, don't blow a brain gasket, that's 12. Right? And actually, you could add these first 4 together. 6 plus 3 is 9. This is 1.5, which is already a 10.5. 10.5 plus 0.75 is 11.25. You already have 11.25 just adding those first 4 terms together. But these next infinite amount of numbers become so small that they only account for 0.75 more of this infinite sum. Mind-blowing. I'm going to stop there. You know, I think I've kind of done enough. You can hopefully understand this as how they approach this as an infinite series. Look at the notes on that, or look up in some Google notes on this. You know, type this: repeating decimals as fractions of integers using infinite series. And you'll see examples of that being done. I'm at 25 minutes, which is a lot longer than I wanted to go, and 25 minutes longer than fourth hour wanted me to go. Goodbye.